Thank you. It's good to be here today. I spent almost my entire career chasing over fraudsters. I joined NICE Actimize 12 years ago. Soon after, my family and I moved to California. Over my many years in Actimize, I was working with many of our clients, including some of the biggest banks in the US, helping them in their unyielding battle against financial crime. Over the years, I witnessed firsthand the remarkable evolution of the field, when both fraudsters and fraud fighters became more and more sophisticated, leveraging top-notch algorithms and tools. And as an anecdote, I can tell that when I joined the company, there were perhaps 2 data scientists, and the title was not even data scientist. Nobody knew what data scientist is. We called them scientists. And now there are tens of different data scientists within Actimize. Last year, soon after we relocated back to Israel, don't ask me why, I got the opportunity to become the manager of the fraud research data scientist team. And today, I want to focus and tell you about one of the recent work that my team was working on, in which we were able to boost performance of fraud detection models by leveraging deep learning techniques. Where is the... Sorry. Okay, so a few words about NICE Actimize. NICE Actimize is a leading provider of financial crime, risk, and compliance solutions for the banking and financial services industry. Among their clients are some of the top banks worldwide, as well as insurance companies and other financial institutions. The bank is sending all transactions in real time to Actimize fraud detection system. And the volume can be as high as several tens of millions of transactions a day. Our fraud detection system calculates a risk score during processing of the transactions, utilizing fraud detection classification models. And then the bank can leverage the transaction risk score together with some other factors using a rule engine system in order to make informed decisions, including declining, delaying, approving, or triggering an alert. So for example, the bank can auto-decline all risky transactions. Traditionally, our fraud detection classification models mostly leverage tabular data, detecting the single transaction. So the system collects and calculates several hundreds of features per each transaction, and that can include both the raw properties of the transaction, such as the amount, the IP address, the payee name, etc. And we can also calculate some reference properties about the relevant entities, such as the account age. The system also stores the history of the relevant entities, so we can calculate, for example, a Boolean flag that differentiates between new and old device, meaning if the customer already logged from this mobile phone or from this web browser. And we can also have some aggregator features, such as, for example, number of distinct devices that the party used in the history. Taking all of that, together with the fraud labels that the bank is tagging, we are able to develop a fraud classification model. Our research experience shows that tree-based algorithms are the most effective ones dealing with the type of data we are handling. And this is in agreement with what is already known and reported in the literature. There are many comparison studies that show that there is a big advantage for tree-based techniques over deep learning techniques for tabular data. So, can we still use deep learning techniques? Is there any room to do something else, something new? Can we incorporate non-tabular data into our modeling system? Perhaps we should not limit ourselves to leverage only tabular data describing the single transaction. Maybe we should do something else. So let's talk a bit again about the behavior of the fraudsters. Usually the fraudsters need to do some work before they can move money from one account to the other. In order to do that, first he needs to access the account. They need to be able to log into the account using some stolen identity or some other techniques. Many times after that, they need to do some more setup actions. For example, they need to add a new beneficiary, changing password, enrollment to a new service, etc. And only later, they're able to actually move the money from one account to the other. This is the execution phase, the last one here. And tabular models are usually focusing on the last phase, on the execution phase, and completely neglecting what happened shortly before that. And that might be too late, because at this phase, the money already left the bank. So even if we will report on fraud, it might be too late for the bank, because they already lost the money. So then we were thinking, maybe we can do something else. Maybe we can leverage the sequence of events that happened shortly before the money transfer event and use it in our modeling. Utilizing data from short history, prepayment has two main advantages. By doing that, we can enrich the model with additional relevant info that we are not using today. And we also have the potential to detect fraud at an earlier time point before the execution phase. So how do we do that? Obviously, we need a model that honors the sequence of events that took place before the payment event. We are doing it by using LSTM neural network. LSTM stands for long short-term network. And this is a variety of a recurrent neural network. So as an input, we are sending to the system the sequences of events in a chronicle order. The neural network will memorize the sequences of events. And as an output, we will get the probability of a fraudulent event. Running a POC, we could see the effectiveness of this method. In this slide, I'm showing the results of one of the first POC we ran. In this case, we used data set of domestic transfer payments that we received from one of our, that we collected from one of our customers. This is real production data. And it is important to note that as an input, in this case, we are only looking at the sequence of events that occurred before payment. We are not using any of the other attributes of the payment itself. And for me, actually, it was quite a surprise to see the effectiveness of this model. We were able to get a very effective model with a ROC AUC of 0.9 for the test data set. So, for example, in this graph, we can see the detection rate, meaning the percentage of the fraudulent transaction that we were able to detect versus the alert rate. So for alert rate of 2%, which is very close to the operational capacity of the bank, we were able to detect approximately 40% of the fraudulent transactions. Going further, we decided to use the output coming from the LSTM model as an additional feature for the tree-based model. And here we can see the lift that we were able to get. On the red line stands for the baseline tree-based model. And the blue line is the same model when we only added one additional feature, which is the output of the LSTM model. The two graphs are showing performance of the same model. On the left, we have performance of the detection rate versus alert rate. And on the right, we have the value detection rate, meaning percentage of the fraudulent amount that we were able to detect per each alert rate. And as you can see, there is a very nice lift. When we took a closer look on the model, we could see that the LSTM model score only 1 more minute. Oh. Does it mean time is over, or I have 2 more minutes? Okay, so 2 more minutes. We found out that the LSTM model was found to be among one of the top 3 features in terms of gain. Also, when we took a look at the shape values, and that gives us the explanation of the model, we can see that the LSTM predictive score, which is the second feature here, was found to be both corrective and risky, which is interesting. So we could use it not only to detect more fraud, but also to improve false positive. To conclude, I think we were able to show and see that by using new technique, but together with also new level of data that we didn't use before, we are able to get a lift on our fraud detection models. And lastly, I do want to thank my wonderful team of data scientists. This is not the entire team, it's only the people that were working on this project, starting with Shubhanshu Sharma, and Gabriel and Michael, that are both here in the audience. Thank you very much. It was all your work.